And welcome back. It's been a little time since our last video. Do apologize for the delay, but just wanted to show you here that we're finishing the top balancing on our two battery packs. Again, you saw the 16 here with kind of the demo of how we're going to apply our compression, along with the original 16 here in our little makeshift holders we were using just to get them charged, as well as top balance this set. Now, once this bank of 16 was top balanced, and then we had this bank of 16 top balanced separately, we then hooked them together and allowed them to top balance as a complete unit. And you can see the meter here. We're down to 0 milliamps. Hope you can see, there we go. Wavering between 1 and 0 milliamps, but pretty much 0 at this point in time. Now, it took roughly, I'd want to say probably about 2.5 to 3 weeks. It started out at about 22 milliamps when we attached the two banks together, and slowly over that time, again, what you can now see from the meter is that there's pretty much no current flow between the two packs at this point. So they are pretty much as even as they will get at this point. What we're going to do next is we'll cut the video here. We're going to bring you into the battery room, and we're going to start the disassemble of the existing battery packs or battery bank that's in the solar room today, and then we're going to get it prepped to bring our replacement banks in there. Look at getting these guys wired up today with, again, what we covered earlier. We're just going to be using our Anderson connectors as a way to quickly connect in and disconnect the packs from the main bank if needed. And then eventually we'll get to the point of putting our long mons in, getting them all wired up, getting our BMS back engaged, and then finally getting these replacement packs wired into the solar system of the house. Now, the old packs that we're going to remove, some of those batteries, or cells I should say, will be decommissioned and will be disposed of properly. Others will actually be maintained, and they may be added back into the into the main battery bank for the house, at least until such a point in time we can get more of these cells. We are looking at getting more of these cells. We're talking to some more distributors in China that we've seen some other YouTubers use, primarily the Off-Grid Garage, Andy, down in Australia. I'm looking at using the same provider that he used for his newer shipment of these 280 amp hour cells. Like I said, we're going to try to get more cells in. And the ultimate goal is to have 4 packs of 16 in the main battery bank of the house. That will give us more than enough capacity that we need to run sections of the house at night, a percentage of the house at night, and only drain the packs to a certain state of charge that we're looking at, and we'll cover more of that when we get to it, and then be able to recover that as well as run the house during the day when sun's out and we're under decent solar production. But that's where we're set. Again, we're top balanced here, we're top balanced here. We've got them connected together in parallel, and again, once again, you can see from the meter that we're top balanced here as well. And yes, you'll notice I'm not wearing my gloves today, or at least for this section of the video, because I'm not actively working with the batteries. But once we get into the battery room and we start tearing the old packs apart, you will see me with a pair of gloves and safety glasses. I can't stress enough, you're dealing with cells that, when hooked together, especially like this in parallel, are capable of a monstrous amount of discharge current. So be extremely careful when you're dealing with these cells, and make sure you're using adequate protection. But we'll bring you back when we get into the main solar room. And welcome back. So you can see the existing battery bank here we were talking about earlier is actually 4 strings of 16. You have a 180 amp hour CA-LB cells. This company is TAFEL. These are 145 amp hour. And on the bottom, you got 2 strings of 16 of these very, very nice 100 amp hour, basically from the electric car parts company. These are meant for EV vehicles. They're capable of a very nice incoming and outgoing charge currents. We'll get a little bit more into details on that because we're going to run some tests on these. But the goal is that we're going to be disconnecting and removing the 4 strings that you see here. All 4 of these strings equal about 515 amp hours worth of capacity, which will be replaced with the 2 strings of 280 amp hour cells that you saw in the garage. That will give us the same capacity that you see here, with a much smaller footprint. What we're going to be decommissioning are going to be these CALB cells, and as you can see, a couple of them have started to swell, but that's pretty normal for those prismatic type cells as they age. Again, they're still perfectly fine. They'll still get the job done. We may reuse these in another project, do some testing with them, things of that nature. But we'll be removing them from service, at least as far as the house is concerned. These cells that you see here, they were not put under compression when they were put in the service, and they had a little bit of bulging issues when they were purchased, hence why they were purchased at a pretty good deal. They have worked fine thus far, but you can see here the nice gap between the final 2 cells there, meaning this cell has actually got a pretty significant amount of bloat to it. So this entire group of 16 will be removed and actually decommissioned and disposed of properly. The 2 strings of 16 that you see here, these will be removed, but the plan is we're going to do some testing with these, because these have had right about a little over a year of constant cycling. So some degree of charge and discharge per day. So we're going to use the tester that you saw in the previous videos in the garage. We're going to grab a couple of these cells, and we're going to charge them up and discharge them and kind of see what our capacity looks like. In other words, how much capacity have we lost in these 100 amp hour cells after having daily charge and discharge cycle. Maybe it'll be a little, maybe it'll be a lot. We shall see. Now, as stated earlier in previous videos, we keep our Batrium, and you can see the long lines for the Batrium here. We keep our battery pack voltage at 3.5 volts per cell. We use what Batrium calls the long life lipo setting, which is a little bit conservative, so you're not stressing the cells by bringing them up to a full 3.65 volts each day. And what will happen is, as the cells hit 3.5 volts, these will start to go into what they call bypass mode. So you'll see a little red light, little red LED will come on. It'll put up to 2 amps worth of a load current per cell in order to start dissipating current in case this one hits 3.5 before maybe this one or this one. So it'll help start bleeding off that current, allowing this one to stay hopefully within that 3.5 range, but then allowing other cells to catch up as needed. So it's, like I said, it's had a year's worth of cycling, both banks, you can see them there, for the last year, every day. The depth of discharge was generally kept to no more than 80% state of charge or 20% depth of discharge. Sorry. There were a couple of days we pushed it a little bit further than that. We went down to roughly maybe about 75% state of charge. But generally they were all kept within going no lower than an 80% state of charge or 20% depth of discharge. But we'll see how all that works out, and then we'll bring you back once we have all this disassembled and have the packs pulled out and getting ready to put the new packs in. Talk to you in a bit. Okay, bring you back for a little bit of an update. As you can see, that we've got our battery packs that were assembled on the top of this table here. Deconstruction removed. Bottom ones have also been electrically disconnected from each other, as well as the main bus bars. It's not critical they move out of the way because the two new packs that we've been working on and testing and have assembled will move on, and both will sit on this top shelf here. Pardon the mess, but a little bit of a aftermath with all the old bus cables removed, and generally between the battery packs, and we'll get into this a bit more of it, but between the battery packs and the main bus bars, and between the fuse holders that you see there for the Class T fuses, I generally try to stick with 2/0 gauge cabling. That's bigger cabling than what we need for our current requirements, based on our inverter here, which you've seen in some previous videos, which is an 8,000 watt inverter, and the most we've ever pushed this to, running 2 air conditioners and about 90% of the house, is about 5 kilowatts. So it's plenty beefy enough for what we're currently doing, hence why 2 gauge cabling handles the amp draw of this guy just fine. But we'll get into a bit more of all this as we get the packs in here and start getting everything reassembled. But it generally tear down is always faster than building it back up. But we'll get you back in here as we progress with this, with getting the packs in the main system. Bring you back in a bit. Bye. And welcome back. Bring you back for a little bit of an update, or at least the last update for this evening / morning. As you can see, we've got our cells that we were working on before in our bank configuration. They're not a battery yet. They will be soon. But per our previous video, we've got just a little bit of mild compression here. Nothing too crazy. We've got our PEX, 1/2-inch PEX tubing installed over our threaded rod, as we spoke about earlier. Now in the previous video, as far as knowing how much compression to put on these cells, it is suggested by the manufacturer to increase the longevity of your cells to add a little bit of compression. But there's no way, at least that I'm aware of, to currently gauge how much compression you should be applying and when you should be applying it. Now they do this at the factory, and they've obviously tested at the factory, but what they're using at the factory, as we spoke about before, is very specific calibrated equipment applying very specific amounts of pressure. Now, since we don't really have a way of mimicking that, I've chosen, like many others, to just kind of use some threaded rod and some angled aluminum with some 3/4 inch wood blocks at either end, as we spoke about before. But in the previous video, if you remember, as far as how much torque to apply, I just applied torque until I could push a cell, and it would, in a sense, push the entire battery bank. Now, I'm going to revise that a bit and just kind of to let you know that I backed off of that. Rather than 20 inch-pounds, I've cranked it down to about 10 inch-pounds. So each one of these bolts that you see here on this fastener is down to about 10 inch-pounds. And yes, you'll notice I'm not wearing gloves. I'm not at the point of going to start wiring the batteries in. But again, you'll see me wear appropriate protection gear when we get to that point. But what we have here is, again, 10 inch-pounds. So each one of these bolts, at the end of these, we held them in place, used our torque wrench until we got about a reading of 10 inch-pounds on all 8 fasteners. Again, 4 on each side. And you'll notice that I'm just going to use my thumb here and kind of push on these 2 cells. And you'll kind of see that I can still move that cell a little bit. It didn't move the entire bank, but it still took a pretty good amount of effort to get those cells to shift out of position. And I'm actually happy with that. It doesn't lock them down to the point that it doesn't give them any room to expand. It gives them a little bit of play that they can still exercise. As these cells, over time, will expand. Also, if you've watched other videos, you may have noticed and heard comments that when they were being charged, these cells actually do get a little bit whiter when they're at a full state of charge versus a narrow state of charge. And Andy down in Australia in Off Grid Garage, he kind of comments on that as well in one of his previous videos. So I wanted to give a little bit of room here for that to play with. But that gives you the updates on what we're doing for our compression here. Again, cranked it down to about half of what it was before, but it still gives a fairly decent amount of compression. And like I said, time will tell whether that actually does in fact increase the longevity of it or causes any, negative repercussions because of it. But what you'll see here, and you'll have to pardon the mess, but it is what it is when you're tearing apart the battery bank and kind of re-engineering it. But what we have so far is that we're just working on basically what will be the DC side of the wiring. We do have our long mons prepped. Just to show you one of these here. Now this is a long mon for our Batrium BMS, which has been zip tied onto a couple of these 3M cable standoffs. And what we'll do is we'll unstick the double-sided sticky tape, and then we'll come into each battery, as you can kind of see here, and we'll stick it in place. And we'll do that for all 32 cells. So those are prepped and ready to go. And what also that we've been working on, you can kind of see here, we've got our Anderson connectors that we talked about earlier. But we're going to do these probably a little bit different than what you would expect. You'll notice there's only one positive line out versus not running positive and negative in these connectors. And the reason why that is, if you look at our battery configuration, this is going to be our positive side of our battery bank. That's going to be our negative. Now, you could run cabling in here and get positive and negative to go in the same connector, but it would lead to a lot of excess cabling, and I'll show you why when we get to the back of our battery bank. So what we're going to do is we're going to have a set in front, which will have only the positive leg running in it, and then we'll have a set in the back, which will have the negative side of the battery bank going into the main bus bars. And I've tried to try my best, and hopefully you can kind of see this. It's late at night, and the light in this room is not the greatest. But also what we've done is we've replaced our main bus bars back here. They were getting a little bit oxidized, more to my liking. I had a better a set that was in better condition than what was here, so we just changed out to those. Now what I'm doing when I'm making each one of these connections, and don't worry, none of this is actually hooked into a battery bank or anything that's live right now. So if you kind of see me touching the insulation on the cables, it's not live. Now good practice would be to always wear gloves at every minute and treat it like it's live, but I know for a fact that these are dead. What we're doing is I'm just taking a little bit of light sandpaper and I'm scuffing the front and the back of this bus bar where the bolt comes through and where each connector is going to mate up. And you may not be able to see that too well, and I do apologize. It's just lighting in the room and it is late at night. But we got our bus bars changed out to more appropriate ones, or I should say not more appropriate but better conditioned ones. And these I actually found on Amazon, and they are actually a fairly thick grade copper, and you can kind of see all the holes that are pre-drilled in it. What these are for is that these are actually meant to be big bus bars for purposes of grounding and things of that nature inside of big telecom equipment. And there's a company out there that I guess that are selling these because I don't know, maybe it was a production run that the end client didn't need after it was done, or whatever the case may be, but these make very, very nice kind of pre-drilled bus bars. And I've pushed these particular thicknesses of these bars in previous versions of our solar system. When we were running a 12-volt system, I've pushed these bus bars in excess of 190 amps. and they've handled it without an issue. I'm not suggesting that you do that. This is not a how-to, but I do know, at least on my setup, they would handle that previously. Now, since we've gone to a 48 volt setup, the most amperage that we've seen the inverter pull, and that's running the majority of the house, gets upward of about 80 to 90 amps peak. So nowhere near what we were pushing before. So these bus bars are more than adequate for our need. Now, the Anderson connectors, and I'll go around the front to show you this a little bit better where the light's better. But on the positive side, each positive one comes down, hits our Class T fuse holder that you see here, comes off the fuse holder, and then hits our positive bus bar. And our negative bus bar is just kind of sitting on the other side of that support post. And let me get back on the other side here to kind of show you this. And again, I got tools and bits and pieces everywhere, and it's just the nature of the beast. So what we have here is that we're going to have a line that comes off of our positive side of our battery bank, comes into our Anderson connector, and then obviously this is our mating connector. Now, the thought behind this is that we're going to snap that in when needed, and it gives us a fairly quick method if we need to take a bank of batteries out of service, rather than happen to, you know, bring a ratchet in or some kind of socket in to undo that Class T fuse, which is bolted in place on those two posts you see there inside that holder. We can, once the system's powered down and in safe mode, we can just kind of grab this connector, pull it down. That'll get rid of the positive, and we can do the same on the back and get rid of the negative. And that will allow us to pull a bank of 16 out of service, do what we need to do. Once we're comfortable with it, snap our connectors back in place, and then we're good to go. And as we stated earlier, you know, these Anderson connectors are quite nice. They use them on a lot of high-powered equipment. I want to say that these are rated, these particular connectors we picked up are rated for about 350 amps, but I've seen much bigger ones. I've seen them used in scissor lifts, electric forklifts, electric pallet jacks, and even the pre-built solar battery systems that you can buy, which has cells and a BMS and everything already built in. Generally, they come out to some type of Anderson connector that you can then take and plug into your existing solar system. So that's our thought behind these. Are they 100% necessary? No, they're not. But it's a method I wanted to try and use in lieu of going over to a battery disconnect switch, which, to be fair, would do the same job. But a battery disconnect switch, and you got to watch these closely like you do with any electronic device or electrical device. These particular switches here, they do have a max rated voltage, and I'm trying to find it on this one. My vision is, there we go, 48 volt DC max. Now, you would look at that and you would think, oh, well, that should be good for a 48 volt battery bank. But remember, 48 volt battery bank, when it's in use and charging, you're going to exceed that. You're going to exceed that by, my system, when it's charging, runs about 56, 57 volts, which will, now, you're not exceeding it by much, but you are exceeding this. So it could potentially lead to problems if internally you exceed its max and something bad should happen. So in lieu of trying to use these, now they do make these in which the voltage range is bigger. This is just a standard like 12 volt marine type one or automotive one you might use to switch 12 volt batteries with. That's why you kind of see a 48 volt max, because they're used with 12 and 24 volt systems. So you kind of have to keep an eye if you're going to be using something like this, and just keep the battery bank voltage in mind. So that's why our thought was just to go ahead and use the Anderson connectors as kind of a means of disconnect. Now again, these, unless it's in the case of emergency, aren't going to be disconnected unless we have turned off the solar system, because you don't want a huge amount of current draw and then pull this out, because it could very well arc across that, or cause an arc flash or something along that nature if you're trying to sever a connection while it's in use and you have a high degree of current. Again, this is for, and I'm going to state this over and over again, but this is for our use when the system is turned off, no current flow, we've got the solar system completely isolated, and then with no current flow coming out of the batteries, we'll pop those connectors loose and do the maintenance that we need to do. This is getting to be a little bit of a long-winded video, and I do apologize, but I wanted to show you the progress of what we're sitting at so far. And then just to show you the back here, you've got a rear set of connectors which will be for the negatives, the main negatives coming off of each bank. They will go into the negative side of the connectors. They'll come out and terminate to that negative bus bar that you saw on the back. Now, you saw this in previous videos, but these are the lugs that come with these particular size Anderson connectors. I have been able to crimp them with this standard, I think it's 10-ton rated kind of hand hydraulic crimper that you can get them. They're all over Amazon. Same type of crimper, various different names, but I'll make a suggestion that if you're going to be using these larger Anderson connectors and using these lugs, to get the bigger hydraulic crimper. This handheld one does do it. You can feel this one struggle. The thickness of these barrels is a little bit much, and the material is a bit much for it, but it can do it. But I would suggest that you get a bigger hydraulic crimper if you're going to be dealing with these. Now you can see the size of this barrel here. It leads to a fairly nice amount of copper that will be inside that you crimp in. And what I've been doing on these connectors, I've been using the number 70 die, and you can kind of see that we've been going through and trying to put about 3 crimps down the length of this barrel. Now again, the crimper does get the job done. You can kind of see it does pinch the sides of it a little bit, but this connector is on securely. We've tugged at it quite a bit, put it under some stress. We took a test one of these and put it under some stress, and yeah, with 3 crimps on this lug, it's not going anywhere. And if you never dealt with these Anderson connectors before, the way they work is that you'll see that this part is flat. It's got a little tab here at the top. What that does is, just to pull one of these off here, you'll see 2 kind of pieces of spring metal in there. And what happens is the flat part of the connector goes up against this metal, and the back part of that tab, that little groove you see there, clips onto here, so that this part of the connector, this little raised, or this little speed bump, if you want to call it that, faces up. So once you have 2 of these connectors created, or once you marry 2 of these connectors together, you'll kind of see it here. I'm trying to do this one-handed, but you kind of see how those connectors line up and then mate with each other. And that's kind of what they'll look like when you take those 2 clamshell halves and clip them together. And with that flat spring inside that connector you saw, it'll apply pressure and push against both of these, maintaining that connection for you. Now, with us only using one side of this 2-sided Anderson plug, what we're going to do is we're going to take the unused connectors, and we're going to go ahead and insert them. You can kind of see me do it right here. And you push them in place till they click. Now, even though this side won't be used, we're going to put them in both halves of the clamshell. That way there's some additional support. So that way when you mate the connector, you get a nice solid connection. And that unused one here, even though it won't be used for an electrical connection, it'll still be there to help maintain that physical connection and help that connector, you know, those two clamshells lock in place. And that's pretty much it for this update. I may call this the first video, and I'll come back and publish a second video when we get to wiring the cells and putting the Longmon monitors back on, and then getting the Batrium set up. But we'll go ahead and get the rest of this low voltage DC taken care of, get these guys wired in, get them into the bus bars, and then we'll put out a second video that will cover putting the banks in series configuration, and then finishing up with mounting the Longmon cell monitors on the sides of the cells, and then reconfiguring the Batrium to only need to recognize 32 cells versus the previous setup where we're running 64 cells. It's been apologize for the long-winded update, but that's where we sit right now, and like I said, we'll see you in the next video. Thank you much.